start the penultimate session of a series of short talks on a variety of topics. And so we're going to have 5-minute talks and then about 5 minutes for question and answer. So hopefully people can have some discussion after each talk, and then maybe we'll have a little time towards the end for further discussion and connecting these talks back with the previous panels. I'll give you a 30-second warning at 4.5 minutes. And so we are starting off with Kimberley Corwin, who's a graduate student at Colorado State. And slideshow.
Okay. We'll see what happens. Okay, hi everybody. I'm Kimberley Corwin, PhD candidate at Colorado State University. Today I'm going to be talking about some of our research on the effects of local and transported wildfire smoke on U.S. solar energy resource availability. And so what I'm focusing on is the irradiance at the surface. So the direct normal or DNI, which is primarily used for thermal solar operations, and the global horizontal irradiance or GHI, which is mainly used for photovoltaic resource assessment. And so we're using data from the National Solar Radiation Database out of NREL for this. And this research followed 3 different scales. The first looking at a series of case studies around California and the wildfire smoke in 2020. I know that there's going to be a following talk focusing more on that. And then looking at comparing a high smoke year versus a low smoke year and expanding to a longer time frame from 2006 to 2021. So I'm only going to talk really about these latter 2 components, which are mainly looking at the baseline or average irradiance available at a monthly scale. So to start off, we compared 2020, which is an extremely high smoke year, which is more indicative of what we are expecting to experience more in the future, compared to 2019, which was a relatively low smoke year, more indicative of what we've experienced historically. And so what we did was we took the NOAA-NESDIS hazard mapping system, smoke plumes, mapped those over the US for this time frame, and computed, well, oh, it buzzed. Okay, there we go. Computed a change in smoke impacted days. And what we see is that from 2019 to 2020, the number of smoke impacted days increased across 72% of CONUS in August and 88% of CONUS in September. That increase was much more dramatic in September, as you can see, with a lot of areas actually experiencing smoke overhead almost every day of the month. We wanted to look at the optical properties a little bit of this smoke. So using the MIAC aerosol optical depth, or AOD, which comes from, which is an algorithm applied to the MODIS satellite instrument retrievals aboard the Terra and Aqua satellites. We found kind of very different changes in the AOD over CONUS during that time frame, with kind of less light extinction occurring in August. The CONUS average AOD increased only by about 23% compared to September, where you saw about 127% increase. So what did this mean in terms of irradiance? So we mapped out the clear sky DNI changes during this time frame, and you can see that there's a pretty substantial change in a pretty severe loss of DNI along the West Coast in California, Oregon, and Washington, as well as in California. So these were driven by locally severe wildfire smoke and led to changes in excess of 20%, 25% loss. And again, this is the average daytime DNI for the month of August and September. These losses in DNI actually persist pretty far downwind, affecting areas kind of as far away as Maine with about a 5 to 10% decrease, and then over north central states around a 10 to 15% decrease, particularly in September. So looking at GHI losses, we're still following kind of a similar pattern, but where you had a large scale loss of GHI near those local fires. But then in terms of the actual transported smoke that was kind of blanketing the country, we saw a much smaller decrease in GHI, generally less than 5%, and in many places less than even 2%. Expanding to look across 2006 to 2021, we calculated our Pearson correlation coefficients for each month of the wildfire season and showed this kind of clear seasonality that peaks with the effect in increasing smoke coverage versus irradiance peaks in August and September. And then we also looked at linear regression analysis on, again, regional smoke coverage. So looking at these 6 different regions across CONUS, and as the smoke plumes in their lateral extent expand, what happens to the daytime irradiance? And for the regional mean DNI, it's definitely more sensitive to the local fresh dense plumes, as you can see in the much steeper slopes in the dark purple, which are the Southwest and Pacific Northwest states, compared to more transported, aged, dilute smoke plumes in the lighter colors. Turning to the GHI, which are the dashed lines, you notice that there's not a lot of change happening with increasing smoke coverage and change in daytime GHI. In fact, the change from going from entirely smoke-free to 100% smoke impacted is about less than 5% again. So I'll go ahead and leave my main takeaways up, and go ahead and take questions.
Wait.
Yeah, thank you. Very interesting talk. I just have a question about the how significant is the impact of fire smoke in general relative to cloud on solar energy?
Yeah, so we did kind of a qualitative look at cloud impacts in our case studies. And so what we looked at was kind of comparing 2 sample days where you had really like thick smoke, about an AOD of 0.56, and thinner, still pretty thick smoke, but thinner at an AOD of 0.43, comparing that to clouds of around a 3 optical depth versus a 10. And what we found was that generally the GHI and DNI impacts of smoke relative to thin clouds were kind of on a similar order, whereas these thicker clouds really can drive much more extensive decreases in DNI. One thing though to keep in mind is that a lot of times these clouds are moving through this area pretty quickly, as opposed to these smoke plumes that'll just kind of sit there.
Thank you.
So really nice application of the hazard mapping system data. Did you just, I know they have like dense smoke and light. Did you look at all of the different categories, or did you look at how that separated out versus dense and light?
We looked at all of the different smoke plumes. So we were mainly looking for, on the NSRDB grid, is there a smoke plume of any density overhead on a given day? Then we were using the MIAC AOD to get kind of a more precise measure of the light extinction than what the binnings and HMS provide.
You can keep thinking about questions. We'll come back and have time for some more questions at the end. And so we'll move on to Tim Juliano from NCAR. Oh, I think this.
Okay, hi everyone. Tim Juliano from NCAR. It's fine. I don't have any notes in here, so the way it is okay. Oh, is it advancing? Okay, we'll just go with it and see. Okay, so today I'll be talking about smoke effects from the August complex wildfires on solar power production in California, and Kimberley just set this up very nicely. So I'd like to thank collaborators who are listed here, and especially Amber Motley at California ISO. So I think everyone here is probably quite familiar with the wildfires occurring over the Western US in 2020, especially during that August and September period that Kimberley just talked about. So here, what I'm showing is kind of a snapshot on September 15th over California, which is where the August complex was really raging. And in this particular picture, you can see that the large-scale flow pattern had kind of shifted from how it originally was. So originally, there was offshore flow driving the smoke over the Pacific. And then at this point in the event, the smoke had kind of propagated up to the Pacific Northwest. And the fire was order 850,000 acres at this point. So obviously, lots of local smoke generation, but quite a bit of transport across not only the Pacific Northwest, but across the entire CONUS, like Kimberley was just talking about. So this is really the focus of this particular study. And of course, one of the primary concerns with wildfire smoke is air quality deterioration and then therefore health impacts. However, of particular interest to this group especially is the effects of shortwave energy and the reduction of solar power production. So what I'm showing here in the top left are observations essentially from or data from the CAISO regions, showing in the top panel the real-time dispatch during the event. So this is a time series essentially in September. So the dark blue line is the solar power production during the actual wildfire event. And then the lighter blue color is just superimposed the climatology for this time of the year. And so you can see pretty clearly in the dashed black boxes that there's this substantial solar power reduction. This is again across all of the CAISO regions. And if we break that down into kind of a temporal look, a diurnal look in panel B, this is showing the difference between the real-time dispatch, so what was actually produced at the sites and expected to go out prior to any curtailments, minus the hour ahead scheduling process. So this is kind of what's expected hour ahead of time from NWP guidance and machine learning during the bidding process. You can see pretty clearly that at least reductions of 10% kind of in the middle of the day, but also in early morning and late afternoon hours, and late afternoon, of course, being very important for demand. The difference is order 30 to 50%. So really substantial, and this was shown in some other recent studies as well. So what did we do? So I'm a numerical modeler. So we use the WRF weather research and forecasting platform, WRF Solar. So it's one of the many flavors of WRF, where essentially, and I can provide more information about WRF Solar afterward, but what we did was we tried to incorporate as best as possible an accurate depiction of the aerosols. And so we're using GEOS 5 reanalysis for this particular study. We incorporate organic carbon, black carbon, and so we really want to look at the effects of the actual event on the GHI, predicted GHI and DNI, versus if we were to use kind of a climatological aerosol data set, which is what's often used in these forecasting applications. So here in the top, in the scatter plot, I'm showing results from our WRF simulations using the climatological aerosol data set, that's in black, and then the data set from GEOS 5, and that's in the blue. So on the y-axis, we have the observed AOD, and on the x-axis, we have the modeled AOD. And all the SURFRAD stations are on the left, and on the right are all the Aeronet stations. And as we expect, there's better agreement. We would hope so. The agreement's still certainly not yet, pretty scattered, pretty scattered. But we definitely capture better the AOD. And then, of course, we want to look at the impacts across different SURFRAD and SOLRAD sites, which is what we use to evaluate the GHI and DNI. And I'm showing here time relative to solar noon. Left is GHI and right's DNI. And this is the solar flux bias going from black to blue is using that climatological aerosol data set, and blue is using the GEOS 5. We still have pretty substantial biases, and this is all sky. There's of course more work to do, and there's a lot of nuance with the aerosols and how you work with the size of the particles and the composition and all of that. But in general, we find that the forecast improves order 50%, and this is across a period from 7 September to 16th September. So with that, I thank you, and I just wanted to show also some work that we did looking at the impact of the smoke in terms of PM2.5 exposure. So I know that this isn't directly related to the energy aspect, but I found it quite interesting. So this is showing the fraction of PM2.5 exposure during this 9-day period. And you can see parts of the Pacific Northwest, large areas over 30 to 40%, actually. So pretty intense exposure. Of course, the August complex was a unique case and an extreme case, but it just goes to show, how detrimental, the smoke impacts can be on human health. So thanks.
Thank you. Questions?
Oh, so Tim, sorry, did I take this from someone? Yeah, Rajesh. Okay. So can your model forecast out, provide solar predictions, including the wildfires in real time?
Yeah, so we use the reanalysis, right? So we were just doing hindcasting.
Yeah.
The goal ultimately is, of course, to be able to do predictive forecasting like HRST smoke, for example. So this particular flavor isn't using active wildfire behavior modeling, but we can use GEOS 5 predictions, for example, to estimate where the emissions will be and how much there will be. So
okay, and then while you're walking up to Rajesh, what do you think your biggest uncertainties are? I mean, where if you had to do one thing to improve your model, what would you do?
Great question. So I think for this, one issue is probably just the resolution of at least what we're using for GEOS 5. That's one limitation. The other one is because we want it to be fast, for operational purposes, the aerosol information that we have in there is very simple. So I think there's just so much variability, especially as the smoke's aging, and there's a lot that can be done there. But again, it's like a trade-off of, how fast you want your model to be versus how accurate you want it to be. So, thanks. Yeah.
Tim, I'm just curious about how you account for the aerosol radiation interactions in this simple scheme.
So we coupled with it's coupled with Thomson aerosol, and then it's hooked up with our TMG. So it's really just through AOD. It's computed in the model. Yeah.
So it wasn't quite clear to me. Were you initializing WRF Solar with the GEOS 5 analysis, and then you were explicitly transporting all those species?
Yeah, sorry,
Okay.
I left out quite a few details there. Yeah, exactly. So we take the GEOS 5 aerosol concentrations for the different categories, and we bring that into the model, and then that is advected around in the model, and
Okay.
It's basically a tracer.
Initialization boundary, but
Absolutely.
you don't have any actual aerosol processes within the model?
We don't. We have time varying emissions, and of course the boundary conditions are time varying. Yeah. And it's all publicly available code. It's in WRF, so it was part of the DOE CETO project, or one of their projects. Yeah.
You showed results against all surf-rad sites or just particular ones in the west?
Yeah, actually all of them. Yep. Yep.
Okay, so all right, because that would water it down, because you don't have as much aerosol over the east
Right.
sites. So did you look at like Desert Rock, which might have been much more affected? And did you do simulations right over the sites, or did you do the whole CONUS area?
Yeah, these are 3 kilometer CONUS. So it's actually a 9 kilometer grid and then a 3 kilometer grid nested inside of that. So the 3 kilometer grid covers CONUS. We did look at individual sites. In the paper, we have like a table that shows the air statistics for all the sites. By and large, I mean, it was doing actually surprisingly well over the Western US. Certainly capturing like the variability nicely, and that's due to the forcing, right? That's if the forcing's bad, you're never going to get it. So certainly the forcing was doing well, but at this high resolution, you're able to capture like terrain effects and all of that. Yeah, thanks.
Good. We will continue our series of smoke impacts on solar. And Maggie Bruckner is a graduate student at Wisconsin.
All right, thank you. So today I'm going to talk about the utilization of HER smoke to infer the impact of wildfire smoke on solar energy. So this work is kind of an extension of some work I did as a LaPenta scholar with NOAA on validation of the HER smoke AOD product, and then have now recently extended it to think about how that might impact, or how the smoke impact might be on solar energy. So HER smoke, as Eric spoke about yesterday, is the addition of a smoke tracer to the high resolution rapid refresh model, and is 3 kilometer spatial resolution over CONUS. And then it uses MODIS and VIIRS fire radiative power to calculate biomass burning emissions and initial plume rise, and no non-fire pollution sources are included. And so I evaluate the first 24 hours of the 0Z runs. And so I looked at the 2021 fire season, where a not as extreme as the 2020 case, but still many large fires in the California area. And then in September 2021, can see kind of large smoke impact over California. So I validated against the Aeronet network, and this network sees all aerosols. And so when I did calculate or remove a kind of background concentration to get AOD enhancements, that when the smoke is the dominating aerosol, we get better agreement between the forecast and the measurement. So here I've got our average bias in the California area for July to September 2021. And then the correlation as well. And HER smoke AOD is on average biased low relative to our AOD enhancement observations. And then I've marked where the Hanford solar ad site is, and we'll look at relating our AOD enhancement in HER smoke to solar direct radiation. The Fresno Aeronet site is the closest, and so now I looked direct to kind of show that we've got, during this time period, fairly good forecasts in this area. The Fresno site captures the smoke enhancements in August of 2021 and September with a fairly high correlation. So now I have interpolated the HER data to the Hanford solar ad site, and can see that during these periods of smoke enhancement, we have decreased direct solar radiation. And then binning that by the AOD can directly see that as our AOD concentration, where we've enhanced AOD due to smoke, we've got a larger decrease in direct solar radiation. And so this could be a potential tool for in real time kind of predicting what the impact on the solar generation might be. So in conclusion, her smoke does tend to underestimate AOD because of the non-fire sources and lack of chemistry in her smoke. But it does capture the timing of the AOD enhancements due to smoke plumes fairly well. And then we can show that the higher smoke AODs result in decreased direct solar radiation. Thank you.
Questions?
Hi, Maggie. So on the last plot that you just showed on the last slide, why does the solar radiation increase for greater than 2 AOD? Going down all the way.
So I think that this is kind of so this case that I looked at, the enhancements were across the July through September period. The maximum is like 3, and so there's just not a whole lot. And there weren't a lot of points where it was above 2. If you look at kind of the, or in this plot, if you're looking at the mean or the median, it does look like it's increased, but overall, the variance of it is decreased. So it is still a downward trend that's probably impacted by low numbers of measurements.
So kind of the same question that I asked Tim, you know, do you know if her smoke is being used for like utilities to forecast AOD and reduction in solar radiation?
That's
I know. Yeah,
it's kind of outside of my area. I was only kind of involved with it for like a summer.
Right on.
And so Rabban Ahmadov would probably be a better contact for
Right on.
asking if solar or if it's being used in that way.
Okay. And yeah. I was
Or
wondering
Eric, if
was
Eric is still
Yeah.
here.
Hi, Eric. Sorry, I don't mean to take it away from you.
So where is Rabban and NCAR?
It's a good question whether it's actually being used. I mean, we still have maybe some utility people in here. Does anyone know if it's used in operations at all for looking at reduction in solar irradiance? Okay.
All right, that's great.
Awesome. Thank you. Actually, I have a question, Maggie. Did you think about looking at we have solar irradiance variables coming out of the HERT. Did you look at comparing those with the SolRad site to see if there's good forecasting of the actual solar variables?
So I didn't quite realize that was in the files because I wasn't looking too much at all the variables, and the extension to the solar part was a very recent addition, but that would be a good next step to kind of take in this.
Okay, great, thanks. Next is Ajoku, now a assistant professor at Howard University, and we have one more talk about smoke impacts on sorry. Looking right at it. Yeah, so there's a laser pointer. Do you want the notes on video?
All right. Yeah, so good morning, everyone. Glad to be here. And I'm gonna try to go through this in 5 minutes, which might be slightly difficult. So the title of my talk today are the radiative impacts from biomass burning aerosols and potential implications for solar energy. The talk that I'm doing today will be mainly focused around Africa. And in case you need my contact info, there it is at the bottom right, or just talk to me later. So just a little bit about me. Thought I'd introduce myself a little bit. I did my postdoc experience here as an ASP fellow. Good times, education. I got my bachelor's in geology, California State University, Dominguez Hills. I got my master's of science in geoscience at University of California, Riverside, and got my PhD in oceanography from Scripps, although I swear to you, I'm not an oceanographer. Current research, impacts of black carbon and biomass burning aerosols on the West African monsoon, aerosol, precipitation, land cover, radiation, cloud feedbacks. It's kind of a tongueful. Connecting inner city communities with climate change, which is not as easy as it may seem. And most importantly, I'm interested in advancing DEI in academia. And to that avail, I have a few personal goals, one of them being diplomacy. There's something called a science diplomat. You can talk to me later about that. Being a research professor, I guess that's checked off. Revamping the education system, and just like Pinky in the Brain would say at the beginning of every episode. So over Africa, season after season, there are fires occurring, but unlike what's going on in the CONUS, most of these fires are small scale, usually done for agricultural purposes, mainly due to slash and burn techniques. So what you're seeing here is an evolution of the fire season over sub-Saharan Africa, starting from January. Let's see. Good old laser. Oh, I think I have it. There it is. There, this is a little lag. There we go. You can't see it underneath, but there's months on there. So in January, most of the fires are happening near the equator over sub-Saharan Africa, and as we transition into August, most of the fires are happening over central southern Africa, south of Congo, near the border of Angola. So now digging into some of my research, what you're seeing here are thermal anomalies or the locations of fires for 2 different seasons. And you're looking at the vegetation types associated with that. And as you can see, just like most places in the world, most of the fires are happening over savanna vegetation types. And I wanted to understand the impacts of this. So this is just an image of a satellite image of how this would look like in terms of thermal anomalies. And this was taken from Worldview. So didn't want to assume that everyone understands the aerosol radiative impact. So I just have like an elementary schematic of the aerosol direct effect. This is assuming that you have clear sky conditions, and just imagine that you're looking east over the continent of Africa, and to the north, you have dust sources, and to the south or to the right, you have biomass burning or fire sources. And usually these aerosols get lofted into the atmosphere, and they get into contact with surface solar radiation, or sorry, shortwave radiation, and this impacts the radiation reaching the surface. On one end, with the absorbing aerosols, you have a depletion of radiation. On another end, depending on the mineral content of the dust, which is important, you might have absorbing air scattering. Nevertheless, this reduces the amount of radiation reaching the surface, and it can actually induce surface cooling. I looked at this at a prior article that was submitted and accepted. And here we're focused for the month of August. Seems like all around the world, August is, well, in the Northern Hemisphere, right? Don't want to leave anyone out. August is usually the month of the highest impact. And here we decided to look at how aerosols impact the West African monsoon. And here we can see that, the sources of aerosols for a month of August over Africa are usually dust and biomass burning. And this is important because I'm gonna try to connect this to PV potential. So here you have the different aerosol sources, and here on the right, you're looking at the precipitation climatology for the month of August. Now here, what we decided to do is we decided to look at how these aerosols impact precipitation, and we classified our data into using composites into dirty and clean days. And what we found out is that when more aerosols are lofted and transported, this actually reduces the amount of precipitation. One of the reasons why that is so is because you have a reduction in the surface radiation. Now, what you're looking at here is a figure showing the observed surface shortwave fluxes for all conditions and aerosol only. And here we can see that the presence of absorbing aerosols accounts for about 50% of the reduction over the Gulf of Guinea and portions of Southwest Africa, at least for this portion of the monsoon. Now, this is a little kind of hand wavy, so just bear with me. So there are a lot of information out there about the photovoltaic power potentials in different parts of Africa. I'm showing here the Middle East and North Africa. Yes, I know biomass burning aerosols are not really prevalent there, but as we all know, dust aerosols are. And the impacts of dust on solar radiation here, as far as I'm concerned, or as far as I understand, is not really being looked at too well. So I really think that this is a potential research avenue that, you know, we should look into. So I just have this little blurb right here. According to the International Energy Agency, Africa has 60% of the world's best solar resources, but only 1% of the solar generation capacity. Something to keep that in mind. And then also, when we look at sub-Saharan Africa, we can see that there's actually quite a bit of potential for obtaining power from the sun, in this case, solar power. And as you can see and imagine, most of this potential is located near desert regions. Now, the reason I want to highlight where I'm circling with my arrow is because that's a source of large-scale biomass burning that impacts pretty much this entire region. So during the summer, and actually including right now, the fires are actually burning in this area, releasing large plumes of biomass burning, not only throughout the local region, but spread all throughout the Atlantic and in some portions of Southwest Africa. So in order to study this, a good colleague, Wenfu, created a grid over Africa using Musica. And I think that this can be a potential research avenue. I have the ideas. I don't have the modeling capabilities at the moment, but if anybody is interested in working on that, I have the ideas. I don't mind writing it up. And I think this can be some good work for the future because Africa is really on the rise, but their scientific capabilities are really minimal. And I'll stop there. I'll take any questions.
In some of this beginning research, do you struggle with data acquisition and finding sparse gaps in data? And how have you attempted to overcome this because you can't possibly put all the sensors out there yourself?
Yeah, great question. One of the hindrances that I'm always dealing with this research is the data availability. It's not really there. So most of the data I use are based on satellite observations, reanalysis data, and model data. There are some AeroNet stations out there, but in terms of the resolution that we need for, you know, accurate data, it's nowhere close. So I really invite anyone here who's interested in possibly writing grants to get more AeroNet sites, even planning a field campaign. I have some really good colleagues. They're actually a part of the Angola delegation that are really interested in this research. So if anybody's interested in sending instruments or even planning a science or research trip out there, I'd be more than happy to talk to you about that. But great question, stuff that I'm still dealing with.
Okay, I have so much, but I'll keep my question to one, general one. And you looking at the AOD and the aerosol from the sky, but particularly I did a lot of work in northern Ghana, and there was a lot of solar panel farms. They had inches of dust on them, right? And so are you looking at the deposition and the impact on the solar? And this would be for any of the wildfires and things like that. You have a lot of smoke deposition onto the panels themselves and how much that reduces the power that you get out of it.
That's such a great question and comment. I haven't looked at that, but when you say deposition, I think about clouds. And I just think about how the aerosols, how fast they deposit on the clouds can actually impact how fast they react in terms of changing the cloud radiative, right? The CREs, which are actually important as well for looking at solar radiation or, you know, solar radiation generation. But I haven't looked at that. But I think that's something we should definitely look at if we decide to go with this study.
Yeah, thank you. So for the field campaign, there is actually talks of planning a field campaign, but in East Africa. So I'm not sure if you are aware of that. Solomon Billing and Will Viswete are leading that effort.
North Carolina A&T.
Yep. And so another question is like, there are a lot of people in Africa who are really interested in research. Are you in connection with some of them? Because there are some local measurements that they are not allowed to access, but maybe if you collaborate with them, then maybe if you share your model simulations with them, they can evaluate it within their constraints.
I hate to say this, but I don't have as many contacts as I would like. I have a few contacts in Angola. I have some in Nigeria, but I'm willing and I'm pretty hungry. Assistant professor
Okay.
trying to get tenure.
Yeah, so I think a report just came out on climate assessment in Africa. I can send that to you. There are 200 people on that, authors on that report. Maybe you can find some important connections.
Yeah, please do, because I have a postdoc coming in and he'd be really interested in that as well.
Just kind of a comment on the deposition of aerosols and dust on solar panels. So there's, we've worked with groups in Kuwait who have a solar farm there, and they found interestingly that the wind did a pretty good job of cleaning off the solar panels. So I think this is where it might be different. It might be, you might have really different characteristics of how dust or smoke particles might accumulate on the panels by region. So it's not a universal thing, but they have a couple papers out showing how this solar farm operated under different cleaning schedules because water is such a scarce resource. So I could point you to those papers too as maybe an aspect of this.
Yeah, I would appreciate that. And you did bring up a good point. These things do vary by region. I'm assuming somewhere like northern Ghana, where it's not as mountainous, the winds aren't as strong, but that adds to the complications, and great point.
Anyone else? No? Great. Okay, thank you. That's all. Okay, so our next speaker is Liz Wiggins from NASA Langley. And thank you.
Thank you. Hey everyone, Liz Wiggins, NASA Langley Research Center. I'm a wildland fire research scientist. I'm also the Center Disaster Coordinator for the new Disaster Response Coordination System. So if you have any disaster response needs as a stakeholder, we're happy to help you out with that. This has been a very informative conference for me. I haven't looked at a lot of the interactions between fire and power before. So it's been really, really great to be able to hear what the power industry actually needs. And I can think of quite a few different applications that maybe NASA can help to develop collaboratively with you guys to help with some of your tough decision making. So my research is going to be very tangentially related to the power industry, but I think that there's some applications here that could be useful. So yesterday, Chris gave us a great overview of geostationary satellites. In this work, I'm using GOES. So for those who aren't as familiar with satellite observations of fires, most of the time people use VIIRS and MODIS, right? Like that's the fire or the satellite instruments that you hear about the most that detect fires, to detect thermal anomalies. So these are polar orbiting satellites, meaning that you get an observation once every 12 hours, more or less, for most places on the globe. And that's great. You get a pretty decent spatial resolution with that. But unfortunately, the overpass time often misses the peak of when the fire is actually burning in the afternoon. And so to try and overcome this, we can use geostationary satellite observations, which, for example, GOES would be a geostationary satellite, or there's a couple of them. And GOES collects observations over CONUS every 5 to 15 minutes. So this is a very, very high temporal resolution data set, but that does come at the expense of spatial resolution. So the spatial resolution of GOES, like Chris mentioned yesterday, is going to be coarser than VIIRS or MODIS, but I think it's still very valuable. So this is a lot of data. This is a big data set. You're talking about data every 5 to 15 minutes over all of the United States. I'll be honest, the data is not super easy to work with. It's given in a weird projection. You got to get it to latitude, longitude. There's issues with, there's a few algorithm issues. There's some issues with false positives. There's issues with smoke and cloud cover contaminated or keeping the satellite from being able to get its signal, you know, all the way down to the surface and back up. So this is not an easy data set to work with. And so what I'm going to share with you today is a way that we have tried to break down this data set for the Western US into more of a digestible kind of a bite-sized chunk. So what we've done is we've created an hourly GOES database for individual Western US fires. And this is using GOES fire radiative power. That's basically just a measure of like thermal anomaly from a fire, or how much energy it's emitting back to space. So the way we did this is we took fire perimeters from NIFC. So this includes fires on all different types of lands. We're looking at everything from fires that are an acre all the way up to the huge mega fires. This covers all different land cover types across the US, or at least most of them. And right now it goes from 2019 to 2022, but we're working on expanding that to present using GOES 18. Most of this is built based off of GOES 17, but we also have it done for GOES 16 as well. So for each of those individual fire perimeters, we went through and we computed the hourly GOES fire radiative power for that fire on every day that that fire was burning, and for every hour that fire was burning. So right now we have over 750 individual fires and a cumulative total of over 7,000 days for this data set. So it's more of a bite-sized chunk, but it's still way too much data. Yeah, I'll keep going, but this is going to be shared publicly, and I certainly encourage everyone to take advantage of it. So after we have the hourly fire radiative power, and basically what that's telling you is from hour to hour, how is that fire behavior changing kind of on a broad scale? That's really great, but what we want to really do is be able to use this data to get at why is the fire behavior changing? Why is the fire spread rate and direction changing or behaving the way that it does? And so a lot of the data sets that we use, especially in fire world, are pretty diverse and disparate. So to try and bring everything together, I also grabbed these 3 different variables that relate to fire behavior. So think about your fire triangle. The different variables that are going to influence that are weather, topography, and fuel. So for each of these fires, for each of the days that it was burning, and for every hour that it was burning, we went through and we extracted the different environmental variables. Like we've got weather, so vapor pressure deficit, wind speed, wind gust, temperature, all different kinds of fire weather indices calculated at an hourly resolution. For topography, we're getting our data from Landfire, which is the database that the Forest Service uses. So we're extracting slope, aspect, elevation, as well as like terrain complexity and terrain variability. And then for fuel, we're also using the Landfire FCCS database, extracting fuel type and fuel load. So the way we did this is basically, this is kind of a dummy example here. This is for the Maria fire. And the black outlines the perimeter, and then this little circle that you see here is a GOES detection, just to give you an idea of how big these detections are. So what we did was, for the centroid of the GOES detection, we treated that as there's a fire somewhere within that 2-kilometer radius circle. So we drew these circles, and then for every day and every hour that the fire was burning, we extracted the data from those circles. So I'm just showing one of the circles here, but you can imagine there's quite a few for every fire, for every hour. And so that gives you an idea of the hourly environmental controls that are contributing to fire behavior and fire spread. And I am happy to add any more variables that you guys know of. So yeah. So once we have all of this data pulled together, we can begin to look at things like diurnal cycle, or basically how is fire activity changing throughout the day, which is really important for smoke forecasting. We can also look at fire spread rate and direction. It's going to be relatively coarse. The pixels are 2 kilometers nominally, so it can get a little bit more coarse than that. So, but we do have an idea of fire spread rate and direction at an hourly resolution. Then we can look in detail at some of the scientifically interesting phenomenon, like the enhanced nighttime burning that we've seen over the Western US. And we can look at extreme fire behavior, or those days when you had really extreme spread. What do the environmental controls look like compared to the fire activity for that day? So all of these results are going to be published soon, hopefully by the beginning of next year. All of the data and code is going to be publicly available and in an analysis ready format. So I'm going to be looking at diurnal cycles. One of my colleagues has used this to look at fire spread rate and direction. So there's, and a little bit on nighttime burning and extreme fire behavior. But there is a lot that can be done with this data set. So I really encourage everyone to take advantage of it and yeah, take off with it. I'm hoping that we can use it for things like, you know, for fire spread modeling. It's really, really hard to do. We have some excellent models that are capable of this, but they're often really computationally expensive. So this is kind of a shortcut way that I see to be able to get a fire spread rate and direction fire behavior on a pretty good resolution just for situational awareness. Yeah, so that's all I have. Thanks.
Hi, thank you. Very interesting work. I have a question on the on your slide on the environmental conditions controlling this fire behavior. So for the fuel, you have fuel type and fuel load. I'm wondering if you consider fuel moisture and dead fuel fraction, and following yesterday's knowledge, maybe vegetation with disease and pests. That might be easier to get on fire.
Yeah, thanks. So yeah. Fuel moisture, I've tried to get at this with some of the fuel moisture fire weather indices. So for example, I don't have it listed on here, but we're also taking fire weather indices from GridMet, which is a 4-kilometer daily resolution data product. So I do have fuel moisture in here. But I would love to have a better data set for that, something that is, I know it's probably not doable except for, you know, by a model, but hourly would be ideal. So yeah, I definitely need to think about ways to bring in more of the fuel moisture. And then as well as the damaged or you know, pest damaged or diseased trees. If you know of any data sets, I'd love to bring it in. I think FCCS does have a few of metrics in there that discuss that, but land fire is not ideal. It's got a latency of like 2 to 3 up to 7 years. So we definitely need a better data set for that. And I think that's a need across all of the fire community.
Thank you.
So before we go to the next question, selfishly speaking, because FRP has been the bane of my existence for like the last decade or so. So I was going to ask, with this application that you're talking about here, how are you handling that from GOES? Because usually the issue is you get several measurements around the fire. You can't get it actually at the fire. So you don't get that actual buoyancy and that heat generated. So how do you account for that? Or how are you planning to?
This is not a perfect data set. So I think when you're looking at a large scale, like one of the larger scale fires, and you take the average across or the sum of the FRP across everything, and then as long as you keep doing that same methodology, you're not going to get perfect FRP. It's not going to be like the true, necessarily the true value of FRP, but you can look at the trends. And so that's what I've really been doing with this is not necessarily for like, you know, if you would go FRP to emissions or something like that. This is more for looking at the way the FRP changes over the course of the day.
Thank you, Liz. This is really exciting. I think from a modeling perspective, this is going to be especially great. I have lots of questions and comments, so we can talk more offline. But I guess for the weather, were you planning to include like her, which is at quite a bit higher resolution than Era 5 or Mera?
I would love to, but I don't know how to work with those dadgum grid files. So if I
have methods, we have methods. Okay.
Okay,
Yeah,
I'll get
yeah.
I'll get in touch with you and add that. Yeah.
So there is a Python package called Herbie that works well for working with grid files.
I will look into it.
Yeah, I can get that link.
This is great. Thanks. Yeah.
Hi, thank you. Super cool. is the pipeline for this data such that it could be expanded into the future? Because it'd be really cool to combine with tempo observations from the trace gases, since the spatial resolution will still be better than that of tempo.
Yeah, absolutely. Great question. So right now the code is written in MATLAB. I know, I'm sorry. But I am transitioning it over to Google Earth Engine, and that's where I'm pulling the data from. So yeah, it'll be posted on Google Earth Engine, and it'll be in a place where you can just draw your polygon wherever you want your detections and hit play, and it'll give you the data. So
Good. All right. I think we need to move on for the moment. Wenfu is next. What did I do? I'm doing escape. Something else?
Inescapable.
Oh, there's a.
Yeah, let's control alt delete maybe.
All right. Well, here I know. I think I
Right.
opened her.
Really? Yeah.
I don't know. We'll figure that out later. Okay. Wenfu Tang is a project scientist in ACOM here at NCAR.
Hello, everyone. I'm Wenfu Tang from ACOM at NCAR, and it happened to me too. Yeah. Let me see. View full screen. Oh, like this. Okay. Yeah, today I'd like to take this opportunity and talk to you about the global expansion of wildland-urban interface, WI and WI fires. So, let me see if anything else. Slideshow. Oh, okay. Okay, yay. Slideshow on. Okay. Thank you. Thank you. Yeah, so what is WI? In short, WI is a geographic area where anthropogenic urban land use and wild vegetation come into contact. Even though the term, okay. Can I do my presentation like this way? Yeah. Yeah, I don't know what happened. Yeah. Yeah. So even though the term wildland-urban interface is self-explanatory, the technical definition can vary according to the purpose. Here I'm showing a widely used definition of WI from USA Federal Register. By this definition, WI include intermix and interface, and here is a detailed definition listed here. So using this definition, there is a WI map developed for the continental US. And on this map, as you can see, yellow is interface and purple is intermix. WI is widespread across the whole country, especially the eastern area and the west coast area. So why do we care about fires in WI? Here I listed a few reasons. First of all, in WI, fire risks is relatively high, and WI fires are closer to humans and properties. Fire emissions from WI fires can be more harmful, and lastly, WI fires will become even more and more important now and in the future. fires in WI is a global issue. If you look at this figure on the left, I'm showing the recent examples of WI fires across the whole globe. And if you look at this map on the right, it shows the research publications relevant to WI from individual countries. As we can see, WI fires is a global issue. However, WI research has only been focused on a few regions. So to study global WI, we use the continental US WI map mentioned previously to train a random forest model to predict WI globally for the year 2010 and 2020. We call the outcome data set a worldwide unified wildland urban interface database, WUWI for short. Yeah, I know it's catchy. So here, listed here are the input data set we use to train the model, and most of them are MODIS satellite land data. So this is the global WI fraction distribution in 2020 from our WUWI dataset. As we can see, in regions without WI file studies, for example, over Africa, the WI fraction is actually very high. And we also compare the 2010 and the 2020 WI files. So on the left, I'm showing the file count fraction within WI comparing to all files. And on the right, I'm showing the fraction of file burned area within WI comparing to all files. And each different color of the bars are a different year. So overall, I would like to draw your attention to the global average. Overall, from 2010 to 2020, both fire count and burned area fraction within WI have increased. Even though, according to MODIS, the total fire count and burned area has decreased slightly globally from 2010 to 2020. And recently, there's another global WI map developed for 2020 using remote sensing derived dataset of building area and wildland vegetation. This dataset is summarized in this nice article. So in this fantastic work, they developed a global WI map at 10-meter resolution for the whole globe. So we compared our results with this study. We found there are some agreement and some disagreement. Overall, it might not be a good idea to use a machine learning model trained over US and apply that globally. So we are currently developing WUWI version 2, which will use this data set for 2020. And we'll train different machine learning models for each individual continents. And with that, I'll stop here with the take-home messages. Thank you.
Thank you, Wenfu. I'm sorry for the technical problems. Any questions?
So first of all, I think that's really, really exciting work, and being able to get a global WUWI is really important. I'm wondering though, as you kind of pointed out, like the definition of urban wildland interface is going to be different in different places. You go back to that definition. Yeah, go forward one. Yeah, I mean, don't we kind of really have to look at the culture of a particular area and think about those definitions in terms of how the landscape and the culture is for a particular area?
Yes, I agree with you. So actually, WI is not a new concept. It has been existed for decades in the fire management community. It's relatively new in air quality community. So even in the United States, some counties might even have their own WI map for practice. And if you look at the definition here, it says houses instead of infrastructure. So that means in this definition, it really emphasizes the houses and the people living in it. So this definition does not include wildland and infrastructure, other infrastructure interface. And also in other countries, for example, in some European studies, they have their own different definitions for WI. I think those are all important to have. Also, I think meanwhile, it's also good to have a unified with under the same definition so that we can intercompare.
Sorry, just a quick question. What's the resolution of the model that you're gonna use for the WUI? That's a nice name. And then next, I would just say, I know it's a standard definition for this right here, but some places that are more remote, like over Africa, you might have areas with 20 houses per square kilometer. And I was just wondering if you like made a new definition, it just might exemplify and magnify the importance of your study, which I think is great, by the way.
Yeah, that's a good point. Also, I was thinking, I'm not sure for based on yesterday's discussion, I'm not sure the tribe region will those be included in this definition. I'm not sure. I need to learn more about that. It is so once we have a unified data set, we can build on that. We can customize according to different regions. And our the resolution of our data set is 8.33 kilometer by 8.33 kilometer. It's a compromise between noise and high resolution because it's derived by machine learning approach. That's a trade-off, and that's the final resolution we can offer. However, in this study, so they developed this map for 2020. However, this study is this map has a resolution of 10 meter. If you want to look at,
Yeah, I just had one. You know, going back to the focus of this topic, you know, and having fire weather models, like not only is this valuable for emissions and air quality applications, but I would think for fire spread models to include that WUI interface and characteristics will be really important for getting fire spread predictions. And particularly, I would expect that that's where a lot of the utility infrastructure is located as well. And so I think, you know, as people begin to look more, you know, develop more better fire spread models, they should include these kinds of land cover information as well.
Yes, thank you.
Yeah, I was gonna say before we go to the next question, which is over there, is that if we could overlay this map with what we were talking about with the power line sector, I think this is exactly something that would be powerful, like Christine was saying.
Yeah, they're already doing the WUIs.
Do you think in a lot of the definitions, kind of WUI is either binary or in the other one kind of tertiary with intermix and interface? Is there any advantage for thinking about more of a spectrum to thinking about WUI in terms of density and vegetation as opposed to just these more simplistic yes, no, or maybe kind of 3 category things?
Yeah. So this is just one of the most widely used definition. Based on your practice and your research purpose, I'm sure you can define other WUI.
Okay. In air quality, we use buffer zones to kind of get away with this, where you just say place it around, and if you're within this distance from the forest or something like that, so that helps.
So we've been dealing with this within the next generation fire system. There's actually more complex definitions of WUI, but then you get into this communication issue. Like, do we need to drill down to what percentage of vegetation, et cetera, when ultimately you want to explain to the public that they're in this wireline interface and they need to be paying very close attention. So at least that's kind of where we ended up, that in some cases maybe simpler is a little better.
Right. I think we should need to move on. Thank you. All right. See if I can navigate this. Oh, no, it works. Okay. Who knows what happened? Our last but not least speaker is Shima Shams, who's also here at NCAR.
Hi everyone, my name is Shima Shams. Thanks for staying up to the last session. So today I'm going to talk about the impact of land management activities on post-wildfire recovery. And before moving forward, I want to acknowledge all of the collaborators that I had in this work. Just a quick outline. It's a short presentation, but make sure we know what we are doing. So we're going to look at some of the project overview to get a full idea of what this pilot project is doing. It has a lot of data sets and methodology, and I won't be able to go over all of those. So it's a good point to just have an overview of them. Then we're going to look at some of the results in terms of the recovery diagnostics and recovery simulation using the machine learning and conclusion. And as I said, this is a pilot project. So the takeaways and next step and plans, what I've envisioned to accomplish. So this project was started when we were working on another work with USGS. And through those, we had interview sessions with manager and planner communities. And while the scope was the importance of land cover and land use in their applications, I recognize importance and the need of understanding post-hazards and the terms of how management activities influence on post-hazards. So that was my motivation to design a pilot project. And so in this work, we want to understand two research questions and see how we can tackle that. First one is, can we quantify the impact of land management activities on post-wildfire recovery using remote sensing data? And I would just want to look at the big picture remote sensing data, what we have available, and then what are the influential predictors on post-wildfire recovery? I used a wide range of data set. I used modus burn products to characterize wildfires in the area and define the boundaries of wildfire over the past 20 years. Then look at the 38 years of Landsat data set to create the time series of vegetation indices to be able to see the impact of wildfire and then how to characterize and diagnose the recovery. And also for the land management, a very well-known established land management data set. So through those, we create diagnostics of recovery. And so that's one result of this work. And then I wanted to do one step more and look into the using machine learning and be able to simulate the recovery. So I used climate data, which was recently developed in Research Application Lab, CONUS 404 in 4 kilometer, and as well as some of the vegetation characteristics and fire specification that was introduced in the data set, in addition to land characteristics and land formation to simulate the recovery. So with that base, I won't be able to go over a picture of all of the data set, but this is very important because many of us might not be familiar with the protected area database, and it's very important to understand the final results. So in this data set called PAD, we have 4 categories of management status, where first 3 categories are managed area and the category 4 is unmanaged. And the 3 first category are different in terms of how they manage the area, especially in terms of disturbance. One allows the disturbance, the other one suppress it, and status tree allows extractive usage. And for the pilot project, I wanted to look at an area that we have a forested area for the most of the wildfire. In addition, having a representation of all gap status in the burned area. So I choose the Northern California, South Oregon for the study. So for the recovery diagnostics, instead of the NDVI, which is known to have an issue of saturation over the recovery, I use the normalized barrier index that use the near infrared and shortwave infrared, which both are sensitive to the health and status of the vegetation. And I won't be able to go over the details, but you can see here that I use the person NBR recovery at year 5 to look at these wildfire. I probably forgot to say, so I looked at MODIS starting like 2004 fires up to 2015 because I wanted to allow 7 years of recovery. So we have some years to look at. So let's look at one of the results that we have. And what we are seeing here is person NPR recovery and then gap status of each wildfire, each group of wildfires that we have. On top of each box, I'm showing the number of wildfire that are in that gap status for the study area. So you can see the most of our wildfires are in gap status 3 and 4. Just a reminder, 4 was the no mandate and 3 is the extractive usage. And we see a significant difference in the person MBR recovery, where gap status 3 is way higher in terms of 5 years MBR recovery compared to gap status 4 with no mandate having the lowest recovery rate. And I was very excited to see the one of the slides of the presentation that we had yesterday that Marco and Belinda showed that the middle, I don't know if everyone can recall. So I'm so hyped that one of the aspects of extension of this work could be looking at a smaller scale, detailed study. But this is for me very exciting to see that larger scale with big picture data, we are still able to see that result. So yeah, so that being said, then I did the machine learning work. We won't be able to go over all of the parameters that are used. So just wanted to quickly show there's a lot that we can discuss here. So on y-axis, we are seeing that the difference of the actual recovery rate minus what we predicted. So the only takeout that I want to see here, point your attention is that when the recovery is in the moderate rate of 30 to 60%, we are able to simulate that with 10%. But for the more extreme cases where we have fast recovery or deteriorating cases, which are more seen at gap status 4, the accuracy drops, which is expected in machine learning algorithm. So in general, we were able to accomplish our hypothesis, and I will be submitting this paper hopefully in the next 2 days. And so we showed that in the area with no mandate for protection, the recovery is more lingering, and we were able to use the random forest for the simulation, which gives us a good result. There are some steps that we are thinking, either like a larger scale expansion of this work, having more detailed categories of management practices and going over how they affect the final results. Another way that I really love to explore is using the WRF-Chem and see how that is impacting the atmospheric composition when we have a slow recovery versus long recovery. So there are different ways that we can explore this. And if you have your ideas, please let me know, and I'd be happy to have questions.
Okay, thanks.
So yeah, I can start if no one else has a question. Yeah, great work. So we've used quite a bit of land cover land use models, such as like Landis, for example, to kind of get at this. What would you say would be the biggest need from a data standpoint to improve your machine learning techniques?
So I guess it depends what is the goal and the scope of the project. So for this hypothesis, we kind of got to what we need. But I feel like the more we can get to the higher spatial resolution and also getting into details of cascading events and really knowing what is the management activity that has been done before, after, and during the process, how we can really see that the impact of flood, for instance, on the area in terms of the recovery, that would be very interesting to look at. In terms of the atmospheric composition, I feel like it's not that much the resolution in the remote sensing data in terms of land cover. We are still behind on the modeling side of the resolution. We cannot really have this much detailed land cover data and characteristics into the model. So that's more on the modeling side on there.
Thank you, Shima. Could you go back to the plot that you had with the results from the different 4 different categories? Yeah. Just conceptually speaking, what does when it drops negative, what does that mean exactly? And is that in the noise? Is that real? Like, what does that mean?
It's real. So in GAPA status 4, there are some areas that they're not going back to the recovery. And that goes to the concept of resilience or the resistance in the area. So it's that basically that ecosystem is pushed to the point that is not going back to the point that it was before. So that the NDVI is, or the whatever index that you're looking at, it drops and then it stays there, or it might go to a deteriorating case.
Now it is. Can you hear me? Sorry about that. I was curious what management data sets you're looking at, and if you're looking at both pre and post fire management to see, plantings versus, fire mitigation effects and that kind of thing.
That's a great question. So this data set, it's pretty defined. So I feel like they probably have both, like in terms of before and after, there are more managed in terms, then there is like a GAPA status 3 and 1 and 2 versus no mandate. But that's why we feel like the next steps of projects are really digging into what they are doing in these managements. And not all of the GAPA status 3 probably are in the same area. So exactly this was just a pilot part to see that, do we see any change to be able to go for the full proposal? But yeah, that's exactly one of the steps that could go.
So I guess before I go to Curtis, I'll have another comment, sorry. So would it be helpful if you had, for example, different management scenario predictions of land cover, land use? Because that's kind of what that model does.
Absolutely.
And we work with the Nature Conservancy to do so. We can talk offline about that.
Yeah, absolutely.
And maybe I'm building off of those past 2 comments, but as I understand your very valuable work here seemed to be applied to coniferous forests. Do you see the ability to segregate that work into forest type or by elevation so that could be applied more precisely to certain areas?
So elevation is already included. I have a land formation characteristics that takes over what is the slope and angle and elevation in general. But the type of forest, that's a great point. We try to just focus on needle leaf forest, but this is MODIS data set. So there might be some, I'm focusing on this area specifically because it's known that there is a little bit more homogeneity in it. But as you said, one of the expansion could be looking at different areas where we have different forest types, and then we could see how the impact of management is different when the type of forest is different.
I was forgotten. If there's anyone online who has questions for any of the speakers, please just speak up. I've been watching the chat, but if there are...
Can I speak up then? This is Peter Nell.
Yeah, go ahead.
Yeah,
we can hear you. Go ahead.
Yeah, so a suggestion might be for other satellite data is also to look at the Copernicus set of satellites from ESA. Sentinel-1 and Sentinel-2, they have a lot of high resolution land data, and I'm sure there must be vegetation products in that. And they're global, so that should be able to use that on top of the MODIS type of data.
Absolutely. So the resolution of land cover wasn't the limiting factor here. It was more of, first of all, in terms of machine learning, I wanted to have like the optimal quick look at it. So I aggregated over the polygons of fire, but also what we are looking here is the management activities. So we should also think about, is it meaningful when we have the same management activity over land that is completely on the same condition? If we look at the higher and higher resolution, what does that mean for us in terms of meaningful results that we get? So that's something that I thought about, unless we have really a test case that on a small scale, we have different management activities and we have different types of vegetation. Yeah, I feel like there is a computational limitations here, and also we could think about how much gain we get out of it when, let's say for the machine learning part, the climate data is, the resolution is still in 4 kilometer in best case. So those are kind of limiting factors.
Okay.
Well, let's thanks all our speakers in this session again. Thank you. Great.